Let's give a few seconds for all the attendees to join. Okay, good morning, good afternoon, good evening to everyone, wherever you are. We are delighted to have you with us today. Welcome to our webinar about mastering rigid inclusion modeling with PLAXIS. I'm Daniel Burro. I'm the product sales engineer for PLAXIS. Today we will have two special guests with us. My colleague and our user, our expert, Richard Vitas, and our user expert, Jérôme Racinier, engineering director of MENAR. Welcome, Richard. Welcome, Jérôme. We are excited to have you with us today, and we are eagerly waiting for your presentation to show on how to model rigid inclusion with PLAXIS. Before we start, I have a question for you about what are the biggest challenges that you are facing in modeling your rigid inclusions. Please answer from these answers. Feel free to send your questions during the webinar. We will try to answer them in the webinar, or we will try also after the webinar by emails. Please, we care about your feedback. It's very important for us. So fill your feedback at the end so we can take it into consideration, and especially your ideas for the future webinar. Let's see the polls. Okay. Sure. As you can see, how to model the rigid inclusion is the biggest one, the biggest challenge that you are facing. So it's great. We will try to tackle it in our webinar, but all of them are pretty not so far away. So now, and the good news is that we will send you an email after the webinar. You will receive an email with a PLAXIS trial request so you can apply what you learned today. This trial will be with the newest PLAXIS version, the PLAXIS 2023 one. What's new with it? The newest release of PLAXIS will contain the trending Barcelona basic model, some temperature and suction in soil test, cable bolt in tunnel designer, rotation failure condition in PLAXIS monopile designer, among other enhancements that you can find on Bentley communities and our LinkedIn accounts, and even you can directly contact me. Now, let's start the webinar. What's on our table today? We will have an introduction to the problematic of modeling rigid inclusion in PLAXIS. We will go through the PLAXIS modeling workflow of rigid inclusions and the MENAR modeling experience on real projects. Okay, Jérôme, now the stage is yours.
Okay, thank you, Daniel.
Yes, the stage is yours, Jérôme.
I will share my screen.
Okay.
So it should come.
Yeah, we do see Jérôme. It's perfect.
Okay, perfect. Yeah. Thank you, Daniel. Thank you, Richard. And thank you, everyone, for joining this webinar. So I am the engineering director of MENAR. So MENAR is a ground improvement specialist. So I will speak today about rigid inclusion modeling, especially for transportation infrastructures. So transportation infrastructure, such as railways or highways, or linear infrastructures. And it's well illustrated by the two pictures shown on the screen. So on the left, we can see all the different geotechnical structures, such as embankment, bridges, excavations, so needed to build a new highway in Germany between two cities. Here it's Mühlhausen. And the total length of the highway is 24 kilometers, and the works are currently ongoing. On the right picture, this picture has been taken in 2013, so during the construction of the high-speed railway in France between Tours and Bordeaux. And with these two pictures, we understand well that the geotechnical design of such linear infrastructures requires the analysis of many cross-sections to consider the varying soil condition along the total length of the railway, to consider the varying geometry of the embankment, but also to consider the different technical specifications. And very often, you know, the technical specifications are much more stringent close to bridges rather than the technical specification away from the bridges. So the use of numerical analysis is very helpful for such geotechnical design, so especially when ground improvement is required. And rigid inclusions is one of the most common ground improvement solutions to support embankment over soft soil. Rigid inclusion allow to increase the bearing capacity, they allow to reduce the settlement. So this webinar is the opportunity to demonstrate how PLAXIS, whether 2D or 3D, can help to design rigid inclusions below embankment. So I would like first to say a few words about what is ground improvement by CMC rigid inclusion. So CMC means control modulus columns. We can see here on this picture a network of CMC installed in Australia to support an access road embankment to a new bridge. The installation of these CMC rigid inclusions requires a concrete mixer truck, a concrete pump, and the rig. So there is a small video, and as you can see on this video, a specially designed auger displaces the soil laterally, and this displacement auger is pushed into the ground till we reach a good layer, resulting in the densification of the surrounding soil. And then during the auger extraction process, a column is developed by growing under controlled limited pressure through the displacement auger. At the end, we get a composite ground improvement system, and the diameter of the rigid inclusion is typically between 250 millimeter and 450 millimeter. Let's now have a look at the design of the CMC rigid inclusion solution. On this slide, you can see on the left the cross section, and on the right, the top view of a CMC ground improvement solution for a road embankment in Poland. The height of the embankment is 9 meters. To come up with such a solution, we need to define the CMC diameter, the CMC spacing, the CMC anchorage. Should we reinforce the CMC at the toe of the embankment here in order that they can resist to lateral displacement? We also need to design the load transfer platform, which is generally granular. Should we reinforce this load transfer platform with geogrids, with steel meshes? That's another question. So it's at the end a quite complex interaction problem. That's why we almost always rely on PLAXIS. We have two options, either using PLAXIS 2D. So in this case, we use 2D elements, so plate elements or embedded beam row elements to represent the CMC rolls. Some initial calibration are required. And the other option is to use PLAXIS 3D and to run a slice model. So that is to say a model which is centered around a CMC row. So CMC here are represented by clusters, so by volume elements. So at Maynard, our strategy, so we mainly rely on PLAXIS 2D models. First, because once the initial calibration is down, we can run all the different 2D cross-section quite fast. And the other reason is that we have much more PLAXIS 2D licenses than PLAXIS 3D licenses. No. Anyway, let's take here the example of a 5-meter embankment over soft clay. So you can see we have CMC with a diameter of 360 millimeter. The spacing between CMC is 2 meter by 2 meter. And we have CMC which are anchored in sand and gravels, 50 centimeter. The load transfer platform is granular. So how to model this case? We always start by a reference calculation, and this calculation is an axial symmetrical model, as you can see here, which is representing by symmetry an infinite network of CMC. So the CMC here is represented by a cluster, and this model represents the behavior at the center of the embankment, and it's considered as the reference calculation. Then we run a 2D plane strain model, with an embedded beam row at the center, and the width of the model is equal to the spacing between the CMC. And the idea here is to calibrate all the interaction parameters between the embedded beam row and the surrounding soil in order to match the results with the axial symmetrical calculations. So in this example, if we look at the vertical displacement, we have the same ones. Here, I've made a cross-section at the boundary of each model to compare the vertical displacement. And you can see that with the embedded beam row elements, I get exactly the same vertical displacement profile. Now, if I focus on the axial forces inside the CMC, we can see that we have exactly the same profile in the cluster element, in the axial symmetrical model, and in the embedded beam row elements. So once this calibration is down, we can go on with the 2D plane strain model. And sometimes, especially when it's required by the checker, we can run on a specific cross-section a PLAXIS 3D model in order to make sure that our 2D approach is reliable. So it's what we have done here, just to show you that this 2D approach makes sense. So I will make a comparison with the PLAXIS 3D calculation. So it's exactly the same model, but in 3D. Let's compare first the vertical displacement. So this is the ISO value of vertical displacement in 2D. And here on the right, you can see the same results with the PLAXIS 3D model. So we have more or less the same vertical displacement distribution. Regarding the horizontal displacement, once again, we have very similar results. We can see that the lateral displacement at the toe of the embankment are quite significant. It's always the case when you have embankment over soft soil reinforced by rigid inclusions. Then it's with embedded beam row, it's very easy to capture the axial forces. So here it's a comparison of the axial forces between 2D on the left and 3D on the right. You can see that we have the same shape and the same values, more or less. And it's the same for the bending moment. So on the left, this is the bending moment coming from the PLAXIS 2D model. On the right, this is the bending moment coming from the PLAXIS 3D model. And we have the same shape, we have the same value. So it demonstrates that the PLAXIS 2D approach makes sense. And another advantage of PLAXIS 2D is that you can run safety analysis in order to have an idea, in order to get the factor of safety against a slope failure. That's also a significant advantage of PLAXIS 2D. So that's.
Thank you a lot, Jérôme.
My side. So yes, please.
Thanks
Daniel.
a lot. No, thanks a lot, Jérôme. Now let's see the presentation of Richard. Richard, the stage is yours.
Yeah, thank you. See if I can share my my camera again. Thank you very much, Jérôme, for this insightful introduction. So what I will be presenting here is I would simply briefly go through all the different steps that Jérôme presented in using PLAXIS for modeling rigid inclusion. I will do it the other way around. I will slightly briefly give an overview of how such model will look like in 3D, and then explain how this PLAXIS 2D plane strain model using embedded beams can be calibrated for the sake of modeling rigid inclusion in 2D. So
Richard,
I will just,
we're not seeing your screen.
Yes, I know,
Yes.
I know. I will show my screen now.
Great.
So I think you should be seeing my screen right now.
Yeah.
So
Now
I decided just to start very briefly as an introduction to start presenting what these 3D slice models looks like. So that's indeed the best representation one can make about modeling rigid inclusion. And I will, just for the sake of highlighting my model. So this is where the rigid inclusion are being placed. You see that spacing. You clearly see that they are right in the middle. So the model width here is exactly equal to the spacing between two consecutive rows of rigid inclusion, such that we can introduce a cyclic symmetry. So that's the model. The rigid inclusion is physically properly modeled using volumes and filled with the proper material. And you see this type of model as well, with the consideration here of a geotextile. We could also have steel meshes, it depends, but in the platform can ultimately also represent in the most accurate sense how the load transfer may operate between the embankment and the rigid inclusion. So usually this is the way such models are being done. However, as mentioned by Jérôme, these models are quite accurate, but requires first having a PLAXIS 3D license and also having experience in using PLAXIS 3D and time to run and post-process the results. So usually many people, especially when many cross sections must be analyzed, prefer to be using PLAXIS 2D. So with PLAXIS 2D, let me open briefly a model in PLAXIS 2D. This is how the same model will look like in a PLAXIS 2D situation, where one can see clearly here that the rigid inclusion is replaced by, or is represented by an embedded beam element, an embedded beam row element to be precise. And of course, because the exact nature of the soil structure interaction taking place laterally, but as well within the mattress, the load transfer cannot be captured properly in a 2D model. So specific modeling techniques and tricks must be introduced in order to guarantee that the 2D model are still accurate. So that's the strategy that Jérôme has presented, which consists first in setting up an axis symmetrical model. So this is the very first model one will be doing. So it corresponds to a single cell, which is represented in an axis symmetrical way, where the rigid inclusion is introduced by using really also here volume elements, or we say soil elements. And the characteristic here is the way the model width, the radius of that model is being introduced. And the model is being introduced, as explained by Jérôme, using here, you see, maximum radius, which is computed such that the area of this model match exactly the area being covered by one unique rigid inclusion in the 2D configuration. So this represents the reference model representing a rigid inclusion in a group situation still. So here there are some specific characteristics of that model. Note here the use of the small extension, although this is not very relevant, but this is something I'm always introducing. And here, if one goes to the stage construction, so I'm first having initial phase, where I just place the solid in place. Then I'm introducing, simply activating the rigid inclusion, and then applying the load. So that's the mattress, that's the embankment, that's the service load, and finally a consolidation. So the reason for that is due to the fact that, well, most of the time the rigid inclusion is going through relatively low permeable material, which is the case here. We have a layer of pit. So the question of whether we should be looking into short-term undrained results or long-term drain results is always on the table. So what is being done here, we are first loading the rigid inclusion in a fully undrained manner, just to generate excess pore water pressure, and then we let that excess pore water pressure dissipate until no residual excess pore pressure remains. And we are doing that calibration exercise based on these long-term results. So once this is done, now we can look at the calculation results, and well, we will start generating some reference results as Jérôme presented. So this will be vertical displacement along the, as well as forces that may develop inside the rigid inclusion. And then finally, also take a look at the skin resistance being mobilized along the interfaces. So those are the three results that one will look into in order to set the reference results against which the 2D plane strain embedded beam model will be calibrated against. Okay, so that would be the second stage of this exercise, to reproduce the exact same configuration, but using this time a 2D plane strain model. So this can be done, and the model then will look like something like this. So this is the exact same model, but this time elaborated in a plane strain configuration. So this is a plane strain model, and this is the embedded beam. And we will use that model, and we will iterate over that model using try and error until we are matching exactly the axis symmetrical model. Then we will consider the calibration to be efficient and achieved. And only then, using those parameters, we will move into the 2D embankment model as presented earlier. So a few important aspects here about being successful in achieving this calibration. Mind first that we need to enforce some kind of load transfer mechanism at the tip of the embedded beam. You need to know that the embedded beam here is just a node. So there is no way a node can properly reproduce the load transfer from the embankment to the rigid inclusion through the mattress. So usually there are two main techniques. The first one is to simply consider a small extension, a fictitious extension of the rigid inclusion in the mattress, which just exists in reality, and to which we will apply a relatively large skin friction, such that the integration of that skin friction over that small length here provides exactly the forces that one wish to have being transferred from the mattress to the rigid inclusion. These values is always provided from the axis symmetrical model, and we can do it this way. So for instance, if you would look here at the embedded beam and the rigid inclusion there, if you look at the skin resistance here, over the first half a meter, we are providing a large skin resistance, which is not realistic, but 550. In fact, 550 multiplied by 0.5 will give you exactly the amount of normal forces you will have to be transmitted. This is one possibility. The other possibilities consist. So that's, sorry, I'm trying to retrieve this one. Well, it's not. Oh, there it is. Sorry, I found it. That's the one. So this is almost the exact same model. The only small difference is related to the way we are operating the transmission. So rather than providing here an extension into the mattress, we are adding here a small stiff plate, the purpose of which is to operate that transfer. And again, the length of that plate is usually being computed again by trial and error until we obtain the proper amount of normal forces at the head of the rigid inclusion. Okay. Then the other remaining important parameter to achieve a proper calibration is to play first with the skin resistance development along the interface or along the embedded beam. So here as well, I am providing here some values. So the value I provided here are directly computed based on the amount of skin resistance being mobilized in the axis symmetrical model, which is always our reference. That's one. And two, also playing a little bit with the stiffness of the interface themselves through the interface stiffness factor. Usually, default values from PLAXIS here do not apply. You need to be playing with those numbers, especially the axial stiffness and the base stiffness, and only then you can achieve very successful calibration in that framework. So I can give you another view of how this looks like. Usually, yeah, you are, and here in that present situation, so I am doing it on the long-term result, and here I'm comparing the match I'm obtaining between this plane strain model, which is the second model I presented, and the original axis symmetrical model. And we have to iterate, operate. Luckily, those models runs very fast in a couple of minutes, and you need to do it this way, understand the main parameters until successful calibration is being obtained. And once you are satisfied with this calibration, then finally you can go and start with the real 2D model as presented by Jérôme there, and then start considering the full problem here and check your design on any suitable cross-section. So here we are using the same techniques, installation, loading, consolidation, and finally here I'm also adding this factor of safety analysis that Jérôme presented. Well, that's the way you will be doing this practically speaking. So this is all I wanted to present. Not taking too much of your time, Jérôme. And before I handing this over to Jérôme again, I was just wondering whether at this stage there were a few questions, Daniel.
Yeah, Richard, I noticed we have a frequent question, which is about if you model the rigid inclusion as embedded beams, what is the best way to input the skin friction?
Well, to input the skin friction, well, that's a difficult exercise. Well, it's again, you need to understand that there is still some limitation in the way an embedded beam can really properly capture the near field solution due to the rigid inclusion source interaction. I mean, it's just a beam. So usually the best way is to always have these axis symmetrical results available and look at the skin resistance being mobilized. And then, of course, if you do the integration of that skin resistance, the shear stress being mobilized times the perimeter of the rigid inclusion, well, you should already get quite close to the skin friction you should, the skin resistance, the skin you should apply for the embedded beam. That's the, and also try to compare it with one can expect to have mobilized simply based on the initial horizontal stress distribution. If you just consider the initial horizontal stress distribution, or the, sorry, not the initial one, the consolidated one, and as well, you start using that horizontal effective source stress applying onto the rigid inclusion, and then just using a simple friction Coulomb law, C plus distress times tangent phi times a certain coefficient, 2/3, a bit less depending on the situation. You might, and then integrate that shear stress, which is fundamentally the QS that one can mobilize along the rigid inclusion, times the perimeter. You should also be with very good order of magnitude.
Great. There is another question. How can we connect the rigid inclusion to the load transfer platform?
Well, that's exactly what I've just been presenting. Two possibilities. The first one, which simply consists of introducing a small extension of the rigid inclusion inside the mattress, which is completely fictitious, doesn't exist, and providing a skin resistance along that small extension such that its integration with the length of that extension provide you the amount of force you'd like to be transmitted. That's method one. And the second one is to add this dummy plate. And again, usually those dummy plates are relatively short, and they are initially computed based on, well, playing with some simple equivalence law, area, and try to compute the area in contact in the plane strain situation and try to compare it with the area in contact in the real situation, and then fine tune a little bit, because until you get the perfect match in terms of normal forces at the head of the rigid inclusion. But that will only give you the head of the inclusion. Then you need to continue the calibration such that the development of the normal force is accurate over the entire element length.
Great. Thanks a lot for the details and for the workflow and for in your answers and in your presentation. Now, I guess we will be back to Jerome. Jerome, we are back to you. The stage is yours.
Thank you. Okay, I'm sharing my screen.
Yeah, we're seeing it.
Okay, perfect. So now I would like to show you two case histories where the design of rigid inclusions below embankment has been done with the help of PLAXIS. And the first example is South Europe project, South Europe Atlantic project, sorry. So a few years ago, as I said at the beginning, a new high-speed railway, 300 kilometers long, was built in France between Tours and Bordeaux. So this is the South Europe Atlantic project, and it allows now to connect France to Spain. And near Bordeaux, so here, and you can see the picture on the right. So near Bordeaux, the railway crosses the Dordogne River. So here you can see the construction of this picture has been taken during the construction of the bridge. The bridge abutment, which is here, the bridge abutment is installed on deep foundation piles, so no settlement at all at this location. And I will now present the geotechnical design of the railway access embankment, which is here. And the height of this embankment is around 10 meters at the connection with the bridge abutment. So let's have a look at the soil conditions. On the left, you can see a cone penetration test, so a CPT, with the tip resistance here in red. On the right, the table summarizes all the lab tests. So, and you can have all the compression values and consolidation parameters which are given. What we can see is that the upper soil layer, which is 7 meters thick, is a very soft and organic layer. That's why we had to consider not only the primary consolidation settlement, but also the creep settlement. And below this soft clay, we have a very dense sand and then a stiff marl. So that's the soil condition. Now, this is a longitudinal cross section. So you can see in blue here the soft clay layer, and you have the embankment. So 300 meters long. So this embankment was divided in two different areas. First, you have the away zone or the regular embankment on the right. So here, the technical specification given by the client is not that stringent. So the total settlement is limited to 10 centimeters at 25 years after railway opening, so on the 30 kPa. With a settlement rate criteria, the settlement must be less than 1 centimeter per year. So for this area on the right, we design rigid inclusion with a diameter of 320 millimeter. It was combined with a preloading fill in order to make some settlement occur during the construction. And the load transfer platform was reinforced by geogrids. Now, if we focus on the transition zone, so the transition zone here is in gray, and it's a transition zone between the abutment on piles and the regular embankment. And here, the technical specification was really stringent. The post-construction settlement was limited to 1 centimeter at 25 years, so total settlement less than 1 centimeter after construction. So we also designed rigid inclusion with this diameter, 320. It was combined with prefabricated vertical drains plus preloading. The idea was to generate as much as possible the settlement during the construction to limit the post-construction settlement. And because the embankment was high, it creates quite significant lateral loading. And so to limit the lateral movement, the load transfer platform was reinforced by steel meshes. So the design was made with PLAXIS 2D, exactly following the strategy defined and clearly explained by Richard, with the first calibration on an axial symmetrical model. This PLAXIS 2D model was done using undrained A calculation, which means that the stiffness and strength of the soft clay layers was defined in terms of effective values. We used the soft soil creep model in order to consider the creep settlement. With this PLAXIS 2D model, we were able to simulate the stage construction with the installation of the CMC, installation of the load transfer platform, plus the 2 layers of steel meshes, the installation of the fill, also the installation of the preloading fill, as you can see here with the dashed line, and then removal of the preloading fill, and application of the live load of the 30 kPa, representing the high-speed train. So here I'm showing you the settlement evolution given by the PLAXIS model. So this is the orange curve. So you can see at the beginning we installed the embankment and the preloading fill. We had very quick settlement, around 11 centimeters of settlement during 6 months. So 6 months is the duration of the works. Then at that stage, we removed the preloading fill and we reset displacement to 0. And it's the time when the railway becomes operational. So we applied a live load of 30 kPa and we followed the settlement during 25 years. And we made sure that the residual settlement was less than 1 centimeter at 25 years. So we also run a PLAXIS calculation using soft soil model instead of soft soil creep. And by difference, we were able to measure the contribution of the creep settlement in the total settlement. So I will show you, here I will show you some picture from the site. So in the foreground here, you can see the vertical drains, prefabricated vertical drains. In the background, you can see the CMC rig installing the CMC. At total, we installed 700 vertical drains and 4,000 CMCs. On the right picture, you can see the installation of the steel meshes panel. So here, the load transfer platform, which is granular, is reinforced by steel meshes panels around here the abutment. So the concrete structure is the abutment, which is built on piles. So this is a picture taken during the works. So here on this picture, you can see the embankment, the 10-meter embankment. So here we are at the location of the abutment, and here the railway was under construction. What is very interesting with this project, and it's not very common, is that we have monitored the displacement of this embankment. So it was possible to make a comparison between prediction and measurements. So the monitoring consisted of 2 inclinometers on each side of the embankment. So you can see the 2 inclinometers plus 6 sensors to measure the settlement here at the center of the embankment. And we had for each pair of sensors, so we had 1 sensor at the top of the CMC, at the top of the rigid inclusion, and 1 in the middle of the grid, in order to compare the settlement of the rigid inclusion and the settlement of the soil. So regarding the vertical displacement, you can see here the dashed line represents the installation of the embankment. So the total elevation is around 11.5 meters, including the pre-loading fill. So this is the total height of the embankment. The dashed red line represents the settlement at the head of the rigid inclusion predicted by PLAXIS. The blue line represents the settlement of the soil predicted by PLAXIS. And the measurements are given by the different points. So what we can see is that the measurements were a bit less than the prediction, but in the same order of magnitude. It's better in this sense. Voilà. The measurements are showing less displacement than the prediction. Regarding the lateral movement, so we had inclinometer on the left side and on the right side. The dashed red line represents the prediction from PLAXIS. And you can see I have also plotted in this graph the CPT, the tip resistance on each side. You can see that the lateral movement, they occurred mainly, of course, in the soft clay layer at the top. The lateral displacement, which was measured, is about 5 millimeters in comparison with a prediction of 10 millimeters. So again, we had less lateral movement than predicted. This is something which is quite common. It's not a problem with PLAXIS, of course. It's just because when we made a design, we have the tendency to be conservative. So we choose the worst soil parameters. We choose the worst thickness. So at the end, we have, I would say, conservative results. And that's a pictures of the railway right now. So that was the first example of a very significant project designed with PLAXIS. Another one here. Now we are moving to Scotland. You can see here the Forth River. We are very close to Edinburgh. And in between 2013 and 2017, the Forth replacement crossing bridge, the red one here, was built in order to replace the existing one. So the existing one is here. This is the Forth Road Bridge. So due to this new bridge needed to work again on the road alignments on the north and on the south of the estuary, and especially on the north part, the access roads embankment, the new access roads embankments run over very weak soils made of soft organic alluvial deposit, which were reclaimed many years ago. So in order to fulfill the technical specification of bearing capacity settlement, ground improvement was required here in the north part of the estuary. So we are moving to the north part of the estuary. And you can see here, it may have a short delay, but here you can see this is a working platform down for ground improvement works. You can see here this is a CMC rig. So the first part of the road here was designed with PLAXIS 2D. It was a quite, I would say, quite usual cross section. It's a symmetrical embankment over soft soil, so nothing very particular. So we use PLAXIS 2D. But now, if you look here in this area, the embankment, the new embankment is shouldering on an existing one. So the cross section is a bit more complex. So it's a bit more tricky. So I will show you the cross section. So here you can see the cross section. So the green line corresponds to the existing ground level. And the final level is given by the black line. So the embankment height is around 10 meters. Very interesting, something I forgot to tell you is that we are here, sorry, we have the former shoreline was somewhere here. So here, this is the former shoreline. So on the right of this shoreline, this is rock. No need for ground improvement. It is pure rock. On the left, this is a part which has been reclaimed with very soft alluvial deposit. So it requires ground improvement. And so the most competitive solution was a combination of rigid inclusion, as you can see, plus trench mix walls. So I will explain a little bit. So the CMCs, they were installed down to the substratum layer, so around 14, 15 meters, in order to provide a high vertical stiffness of the foundation soil. And these trench mix walls, the hatch red block, so it's trench mix walls, they were installed every 2 CMC lines, I will show you later. And the only purpose of these walls was to provide a high horizontal stiffness and to intercept potential shallow slip circles. And they were installed to only 6 meters deep, so they were stopped in the soft layer. So a few words about trench mix. So on the right part of this slide, you can see the trench mixing rig. So trench mix is a deep soil mixing method which consists in the formation of trenches or panels of soil mixed with a binding agent. So it's mixed with a grout, with cement. And under the action of the chain that you can see, the soil is broken up and mixed with an hydraulic binder. And like this, we get at the end a soil mix material, which is homogeneous, uniform, and with quite a strength which is better than the original material. And for this project, the UCS value, so unconfined compressive strength of this soil mix material, the targeted value was 800 kPa. So let's have a look at a top view, just for you to understand, and I will zoom a little bit. So this is the top view. So you can see in green, this is the former shoreline. So above, it's rock. And just below here, you can see this is the reclaimed material. So you can see the CMCs. And in between the CMCs, you can see the trench mix panels. And at the toe here of the embankment, you have a sewer. So it's a very complex geometry. And that's why we decided here to go with PLAXIS 3D. So we represented a PLAXIS, I would say a trench model, a slice model, in order to represent at the same time the trench mix panels, the CMC's rigid inclusions, the sewer, the geotextiles. So with this PLAXIS 3D model, we were able to represent everything. So you can see here the red part is the rock. So and on the left part, you have all the soft soil layers. So everything was represented. We were able to measure, to predict the vertical displacement, the horizontal displacement. And also, we looked at, of course, the CMC integrity. So we were able to look at the axial force inside the CMC, bending moment inside the CMC. And we were able also to look at the normal stresses and shear stresses inside the deep soil mixing. So this combination, just to make things very clear, The CMC were down to provide high vertical stiffness, and the trench mix panel were down in order to provide high horizontal stiffness. And that was a successful project. And then the new bridge, the Queen's Ferry Bridge, was opened in 2017 by Queen Elizabeth, as you can see here on this picture. So the works we done were just before the access it was the road access embankment to this new bridge. So as a conclusion, the design of rigid inclusions below embankment is a quite complex problem because it involves many interactions. So between the load transfer platform and the rigid inclusions, between the rigid inclusion and the surrounding soil by friction, between the rigid inclusion and the anchorage layer. And the design of rigid inclusion also imposes to verify the structural integrity of the rigid inclusion. So to look at the axial force, at the bending moment. So all these interactions, they can be evaluated directly by PLAXIS model. So that's why PLAXIS 2D and PLAXIS 3D offer us very valuable tools for rigid inclusion design, so especially below embankments. So that's two examples. So that's the end of my presentation.
Jerome, we have a question I noticed. How do you model the steel mesh panels with PLAXIS 2D?
Yes, so it's quite easy actually. We use a GeoGrid option. So we use GeoGrids to represent steel meshes panels, and we adjust the axial stiffness of the GeoGrid elements to represent the stiffness of steel. So GeoGrid elements with the stiffness of steel.
Mm-hmm. And another question, how do you extract the axial forces and bending moment in CMC rigid inclusion for a PLAXIS 3D model?
Yes. If we take the example of the last case history in Scotland, we ran a PLAXIS 3D model, and so the CMC, the rigid inclusion, were represented by volume elements, by cluster. So what we generally do is inside this volume element, we had a beam at the center, and we give this beam axial stiffness and flexural rigidity equal to the one of the CMC, but divided by a factor of 10 to the power 6, by a huge factor, in order that this beam do not modify the result, do not impact the result. But at the end, it's quite easy. We can use this beam to to plot the axial force and the bending moment, and we just need to multiply the results by the factor of 10 to the power 6 to get the result. So that's a trick, I would say, to easily capture the axial force and the bending moment in volume element just by adding a beam inside. But maybe Richard has other options to do it.
Thank you, Jerome, for your modeling experience with the real projects. It was a big plus. Thank you, Richard, for the PLAXIS workflow details. It was really great. I'm sure it will guide our existing and future PLAXIS users. Please don't forget about your feedback at the end, especially regarding the new topics for the new webinars. Thank you for attending. See you soon. Have a good day. Bye-bye.
Bye-bye.
Bye-bye. Have a good day.